Thank you. Good morning. Okay, so I'm gonna, this is gonna be a very kind of brief thing. I had a much longer presentation, but it ran like 50 minutes, so I had to cut about 60% of it off. So I apologize if you find this to be too brief and short on details, but it is what it is, right? So we're gonna start with some history, and then we'll finish with where we see the future going, okay? So, as far as here, I have talked past, present, and future. So I had to kind of divide it up with what I think is the past, what is the present, and what's the future. So the break point for past is until 1999, and you'll see in a minute why that is. Okay, the present, 99 till now, and the future, well, we'll talk about that at the end. All right, and I want to compare essentially conventional bridge design versus seismic isolation, okay? So if we look at up until about 1999, people doing conventional bridge design have had a lot of guidance. Started ATC, Seismic Design Guidance for Highway Bridges. That was published in 1981. Caltrans published MTD 20-4 in 1990. That was like about a year after the Loma Prieta earthquake, and that provides all kinds of guidance about retrofitting bridges, okay? AASHTO LRFD BDS Bridge Design Specifications, 1994, right? ATC 32, Improved SDC for California Bridges. So a lot of guidance for conventional bridge design. If we look on the isolation side, there's a couple of handbooks that have a section on seismic isolation, one by Naeem and one by Priestley, and they just have a section in the book, not a very long section about seismic isolation. And also in the same period, you find a couple of textbooks, one by Skinner and one by Kelly. Again, these are textbooks. So if you compare conventional bridge design versus seismic isolation, you can see that people doing conventional bridge design had a lot of help. Seismic isolation was kind of out there, okay? Now, why 1999? Again, in 1999, especially on the seismic isolation, the guide specs came out, the AASHTO guide specs. That's the first edition. Of course, it got updated, and we're on the fourth edition, 2014, right? On the conventional bridge side, Caltrans published its seismic design criteria, the first edition, and of course, that went through, several updates. The last one was January of 2025, okay? Also on the seismic isolation side, Dr. Buckle and a number of other researchers, Professor Disleli, they put out a companion report to the AASHTO guide specs to provide more guidance, more examples, and so on, right? So that's, again, why the 1999 was kind of a turning point for seismic isolation. All right, so I'm going to talk about, essentially the past in California bridges, okay? SRMDs essentially started being used in California bridges as part of two major retrofit programs, okay? After the Loma Prieta earthquake, Caltrans identified 1,039 bridges for retrofit, okay? And then after the Northridge earthquake, another set of bridges, 1,209 bridges were identified for retrofit. So essentially, you're talking about 2,200 bridges that were retrofit in that period, okay? Retrofit techniques, right? Column casing. You go or drive around the state, you'll see a lot of those. They're visible. Enlarged foundations. You won't see it, but that's also another retrofit technique. Seat extenders, again, hidden, don't see them, right? Foundation strengthening. Seismic restrainers. You can see those driving under bridges with steel superstructures, okay? Component strengthening also, especially for bridges with truss superstructures. And response modification devices. That's seismic isolators, dampers, buckling restraining braces. But, out of 2,248 bridges, only 30 saw seismic isolation, okay? So, question is why, right? Well, again, the history hopefully gave you an idea of partly why, because there wasn't a whole lot of guidance. Designers were sort of out on their own. They had to rely on textbooks. I worked as a designer for many years. We don't really rely on textbooks. We want codes, we want, design aids, design guidance, and so on, okay? Other issue, not problem, the other fact is that most bridges in California are box girder bridges with integral columns, right? To do seismic isolation on a bridge like that, you essentially have to decouple the superstructure from the substructure so you can add the seismic isolation, for instance, right? That can be an expensive proposition, right? So, bridges, those 30 bridges that I mentioned, they had one common feature, right? They all had steel superstructures, okay? With the exception of like a single span bridge, which was concrete, so they put, it's a single span bridge, so already decoupled from the substructure, so they added isolators to it. But the rest of them, they're steel superstructures. They're already decoupled from the substructure, and so, adding isolators could be as easy as taking out the old bearings, which probably will fail, and then putting an isolator bearing in their place, okay? Now, again, for these structures where the seismic isolation, for instance, was used, they were done for, some reasons here. One is conventional retrofit just wasn't feasible. That would be one reason, okay? Another one is that conventional retrofit was just too expensive. When you have some of these bridges are over water, and to do a conventional retrofit, not only do you have to strengthen the piers, but you got to strengthen the foundation. A lot of underwater work, okay? Sometimes performance goals cannot be met with conventional design, so then we go to seismic isolation. There was also dampers used on some bridges, okay? So these were used to essentially limit longitudinal displacement in the bridge, okay? Also for these suspension bridges that use dampers, they were introduced or added to the bridge to reduce the obviously avoid the pounding between the suspension span or the stiffening truss and the towers, but also limit the force that can be transferred to the tower, okay? So I want to talk in a little more details about all these bridges that have been, designed or retrofit with seismic isolation. So it's kind of the past and the present, okay? So if I've come up with 36 bridges in California that have seismic isolation or response modification devices, not just seismic isolation, okay? So out of those 36, 8 use friction pendulum bearings, okay? So, of course, one is Benicia Martinez that was retrofit in 1998. So this is kind of the main spans of the bridge. And in the upper left corner there, you see the bearing. That's a pretty big bearing, although it doesn't look that way in the picture, right? American River Bridge. This is a new bridge that was built or completed in 1997. Okay, this one used, again, friction pendulum bearings at the top of the columns. So essentially, this bridge, although it looks like an arch bridge, those are actually fake arches. They're not structural. They're not holding up the superstructure. And so to keep them elastic, they had to isolate the superstructure. And so the superstructure is just floating there on top of the columns, okay? Another one is the Antioch Bridge, okay? Again, this one used the single friction pendulum or single friction surface pendulum bearings. And they considered, I think, 7 alternatives for retrofitting this bridge. And seismic isolation was by far the most economical solution. Another one, 6th Street Viaduct, right? This is in Los Angeles. These are arch bridge, designing arches to respond basically inelastically. At the time, this is oversight by Caltrans. Caltrans set a limit of no more than the ductility of 2 or less ductility demand that is on the arches. That just wasn't feasible. So seismic isolation came in rather handy there, where the substructure is isolated from the arches. The arches can be designed for the gravity loads, and the isolators essentially limit how much force is imparted to the arches, and they can remain elastic, okay? So lead rubber bearings, 22 of those 36 are lead rubber bearings, okay? Sierra Point Overhead Bridge. This is the first bridge in the US to actually be seismically isolated. So not 1975, but 10 years later, right? So this is what the bridge looks like. It's a simple bridge, steel superstructure, okay? The existing rocker bearings were replaced with rubber bearings. Some were square, some were round. Now you'd expect the lead rubber bearings to all be round, right? But back then, for some reason, they had both on the same bridge, okay? Rio Vista Bridge. This, I think, the retrofit was completed around 2000. This is actually my first project out of school. After I graduated from here, I went to work in San Francisco. I got to work on this project. So, underwater foundation requires expensive retrofit, but we came up with the solution of using seismic isolators, which avoided actually any foundation retrofit. We just had to enlarge the seats a little bit to accommodate the bearings, and then everything was good, right? Coronado Bridge, again, of trying to avoid foundation retrofit. Again, seismic isolators, lead rubber bearings came in. They're handy there, okay? So that's the friction pendulum, lead rubber, right? Dampers. There's 5 bridges that have dampers on them, okay? And this one is actually a new bridge. It was built in 2000. It's an overcrossing. It's a 2-span bridge, but dampers were added at the abutments in about 4 dampers at each abutment. Okay. San Francisco Oakland Bay Bridge, the West Bay. So that was, it's got 2 dates, 1996 and 2023. That was essentially equipped also with dampers. First batch was installed in 1996. They started leaking, and it got to a point where they needed replacing, so 2023 is when the replacement project was completed. Vincent Thomas Bridge, again, 2 dates, 1996 and 2017. That also had to have the dampers replaced, okay? So this is kind of the dampers on a Vincent Thomas Bridge. It had 40 dampers, and when we did the damper replacement project, we had a number of other things that we needed to fix on the bridge, but we replaced all the dampers. But in that process, we essentially introduced also buckling restraint braces to this bridge, okay? So, and that brings me to the buckling restraint braces. 2 bridges used buckling restraint braces. First one was the Auburn Forest Hill Bridge, 2014. And the second one, that's the Auburn Forest Hill Bridge. It's a very tall bridge. It was built so high because there was a provisions to build a dam, which was never built, okay? And then, of course, the Vincent Thomas Bridge, and this is kind of what it looks like. So on the Vincent Thomas Bridge, there was a study in UC San Diego a while back looking at what would happen if you just replace all the dampers with buckling restraint braces. And they kind of concluded that it was feasible. But we looked at it when we were doing the what we called it a refurbishment or damper replacement project. And these BRBs would have to be, I don't know, 40, 60 feet long to accommodate the displacements that were required. And then the forces were too high, so we couldn't really design them. So we kept pretty much all the dampers. So out of 40, we replaced 32. And then 8 dampers, which are in a sort of backspan fuse. These dampers don't move, so we replaced them with buckling restraint braces. So it was just an opportunity to try out something different. And I look at buckling restraint braces are like a low-cost damper. No maintenance, Problem with that is when you get the big earthquake, you probably have to replace it. With a damper, maybe you don't have to. But anyway, so for both of these bridges, the problem with leaking dampers was that had to do with essentially ambient movements. That the seals on these dampers, they have a life, but they were seeing a lot more than anticipated because of ambient movements. Just vehicles going over the bridge causes the suspension span to sway, and that causes the dampers to essentially move, okay? So what was done then on this replacement projects on both bridges is to isolate the dampers from these ambient movements. And in one bridge, in the Bay Bridge, they used sort of a device internal to the damper called lost motion device. And then on the Vincent Thomas Bridge, we did an external solution, which is in the damper brackets where we allow the pin to just move freely under ambient displacements, and then it would only engage in extreme temperatures or in an earthquake. So Vincent Thomas was finished in 2017, and that is the replacement project. So far 8 years down, 8 years on, we haven't seen any problems with the dampers, okay? Now I want to just go a little more details on some of these bridges. And again, like I said, they had 50-minute presentation, so I cut a whole bunch of it out. So this is going to be very, very brief. Okay, so first one, again, this is the first isolated bridge in the US, right? built in 1957, retrofit in 1985. Okay, design spectrum had a 0.6 PGA. You can imagine these are old columns with poor confinement, with lap splices at the connection to the footing, poorly reinforced footings, right? So trying to fix, to use a conventional approach would have to essentially fix the column and fix the footing. So instead, the existing rocker bearings were replaced with isolation bearings, okay? So that's an example there. It's a square one, but like I said, there's a mix of square and round ones in the bridge, okay? Also, restrainers were added at the expansion joints. You know, this is a steel superstructure, so you have expansion joints at every bend. And so to keep those expansion sides from falling off, they were tied all together with restrainers, okay? So this bridge is actually instrumented with accelerometers, and it saw the 1989 Loma Prieta earthquake. The earthquake is about 100 kilometers away from the bridge site, and the measured acceleration on the bridge was roughly about 0.3 G, okay? And there was no damage reported on this bridge, okay? Next one is Benicia Martinez, right? Has the world's largest friction pendulum bearings, unless they've made something larger. I'm not aware of it, right? You know, EPS might have a different opinion. Okay, so this bridge was designed as a lifeline structure, okay? It's basically designed to remain open after a major earthquake. It's not going to close. I mean, you may have to do some temporary stuff, like at expansion joints, something like that, but the bridge is essentially designed to remain elastic, okay? Again, that's under the design earthquake, right? Existing bearings were replaced with single friction pendulum bearings, right? These bearings had a 13-foot diameter, so that's the largest. Each isolation bearing weighs about 40,000 pounds and can move 53 inches in any direction. And that's kind of the bearing, and the person back there gives you a feel for how small that bearing is, right? Okay, hasn't experienced any major earthquake yet, so we don't know how it will actually do in a major earthquake. Okay, and then another last example bridge here is the Smith River Bridge, okay? This is currently under construction, okay? This is the first Caltrans bridge using triple friction pendulum bearings. Now the 6th Street Viaduct I mentioned earlier, that was the first one in California, but it wasn't a Caltrans bridge, it was a City of LA bridge. This one is a Caltrans bridge, okay? It has 10 isolators in it, 5-foot diameter at the abutment, 6-foot diameters at piers. These are, triple friction pendulum bearings, okay? So why seismic isolation? You know, why not just do conventional like we always do, right? Well, this had a challenging bedrock profile, okay? The rock starts at about 150 feet below ground at the beginning of the bridge, and it's pretty much at ground at the end of the bridge. So how do you do, you know, stiffness balancing on a using conventional design? That is quite the challenge, right? And also, you know, the choice of isolation here gives you a smaller footprint in an environmentally sensitive, environment area. Smaller footprint is a big plus, okay? So again, the bridge is currently under construction. Just a little picture from construction there. You can see the bearing there on top of the pier, and there they're starting to form the superstructure, and I'm told that they're already getting ready to start post-tensioning the superstructure, so this is obviously a much earlier picture than what the bridge is at now, okay? All right, so we're gonna talk about the future of SRMDs in California bridges, and this is gonna be based on this DES SSIP, right? This is a document that was published in June. It is the Seismic Strategies and Implementation Plan. So this is our plan, Caltrans' plan, or more specifically, Division of Engineering Services plan of what we're gonna do about seismic engineering or seismic bridge engineering in the next 3 to 5 years, okay? So, so the aim of the SSIP is to make the use of SRMDs, and especially seismic isolation, part of everyday practice. We're gonna bring it to ordinary bridges. We don't want special bridges anymore, right? So, and this is, you know, the DES Structure Policy Board has essentially a goal to increase the use of seismic isolation in new bridges and also for retrofit of existing bridges. So we wanna consider seismic isolation as an option every time we're dealing with a bridge project, right? Why do we want to do that? Well, Caltrans has goals, has, many goals, and some of them are, improving safety, climate action, and prosperity. And seismic isolation can help in that regard, okay? Seismically isolated bridges perform better than conventional bridges. Some people may have a different opinion on that, but that's my opinion. I'm sticking by it, okay? So that means lower safety risks, right? Seismically isolated bridges have lower potential for needing extensive repair replacement after a major earthquake. If you look at AASHTO, the seismic design requirements, it starts out by saying a bridge designed by the code could need major repair or even replacement, okay? So with the seismically isolated bridge, you don't actually have to do that, right? So this improves the resiliency of our transportation system, right? Reduces carbon emission. If you're not repairing bridges or replacing bridges, you're going to be doing less construction, right? And of course, you are going to lower the life cycle cost, meaning you get more bang for your buck, right? Okay. So again, that's the goal, right? Why haven't we done that, right? Well, there are barriers that need to be addressed and removed so we can actually achieve this goal, right? Design requirements. If you look at the current SDC, it says a bridge with seismic isolation is a non-standard bridge, therefore it needs a PSDC, or a project-specific design criteria. So that already, puts most engineers off, okay? Also, lack of design tools, design guidance. I kind of did that history there to show you how much the conventional designers have at their disposal versus the seismic isolation designers. So, within Caltrans, we have a whole set of documents of design details, design guidance, design, and those documents are for conventional bridges, not for seismic isolation, right? Also, when you're trying to select a bridge type, you need a good cost estimate, and with seismic isolation, we don't have a whole lot of experience, so the cost estimates are sort of, I don't want to say guesses, but they're not as good as a cost estimate that's done for a conventional bridge, because we've built a lot of conventional bridges, and the estimating branch, that's how they price bridges. They look at cost of construction on other projects, right? So, all right. And again, life cycle cost. If you want to talk about life cycle cost, there's not really a whole lot of data, at least as far as we see it, okay? So how do we move forward? So that was the problems. How do you move forward, right? Well, we're going to actually initiate a pilot program to select 10 bridges in high seismic areas and actually design them with seismic isolation. We're not going to do type selection on them in a sense that they will be designed and built with seismic isolation, okay? So the other thing we're going to do is that all new bridges that come up for type selection or for retrofit, existing bridges for retrofit have to consider SRMDs in general or seismic isolation in particular in their process. So they have to show that, that some other method is more desirable than seismic isolation before they could just go with it, okay? And of course, right now, most type selections are just for conventional bridges, and the type selection panel doesn't, sometimes will ask, have you considered seismic isolation, but most of the time they don't, okay? So, well, I think I kind of said that already, right? Didn't I? So, and the other thing, the problem I talked about, PSDC, right? We want to get rid of this PSDC business. We want to essentially incorporate seismically isolated bridges into seismic design criteria so that it becomes, again, as far as designers, they don't see it as some special bridge that now they got to deal with a special problem, right? Also, like I mentioned, Caltrans, we have a whole bunch of design documents that are for conventional bridges, and we need to incorporate seismically isolated bridges into those design documents. We have bridge design aids, bridge design practice, bridge design details. We also have a standard bridge details. All of these are not for seismically isolated bridges, and we need to essentially include them. And, an alternative would be to create a parallel set of documents for SRMD bridges, okay? And, right. So, of course, we generate all these documents, we generate all these requirements, but until you train the engineers, you know, it's not necessarily going to get implemented. So we will have a training program integral with this goal, okay? And we also want to fund research to fill essentially knowledge gaps, right? Currently, we have a project with the UCSD looking at seismic response for beyond design level earthquake. We have our document, design document, essentially BDM 20-33, stipulates that columns have to be a secondary fuse. So the question is, well, what do you design that secondary fuse for? So hopefully this project will answer that. And it looks like I'm out of time, but I'm also done too. So potential future research topics, very quickly. Impact of vertical acceleration on isolated bridges, right? Response spectrum versus time history. When do you have to do one or the other? Can we expand the range of applicability of response spectrum analysis? That would also simplify things, right? And design guidance for using dampers. There's really nothing out there that a designer can rely on, so that would be another good topic, okay? And that is that. Looks like, all right.
Fouad, thank you.